Hello, everyone.
Hello.
Welcome to the seminar series. So today it's my pleasure to introduce today's speaker, Andy Newman, Dr. Andy Newman. He's a project scientist 3 at NCAR, someone who embodies the spirit of interdisciplinary science, right?
Yeah, thanks.
That's the rumor anyway.
Yeah.
So, and furthermore, I just made all this up. Andy's career has been shaped by his deep curiosity about the natural world and a drive to make weather and climate information, now more important than ever, more useful to society. From his early days as a self-described weather geek to become a national leader in regional climate modeling, hydrology, and convergence science, Andy has built tools, data sets, and partnerships that are now foundational across multiple fields, from water resource management to public health. Okay, so today's...
I think the talk's going to be a letdown after that.
You are the star of today. So today's talk, Navigating the Research Currents from Weather Geek to Interdisciplinary Scientists and Beyond, captures both the arc of Andy's own journey and the broader evolution of our field toward integrated, actionable science. So please join me in welcoming Andy Newman.
Thanks for the great introduction, Scott. See if I can try to do that justice. Really honored to be here today. Just have a lot of gratitude and good fortune to kind of be in this position at this point. So yeah, I want to thank everybody online and in person. I do really appreciate the chance to talk to y'all. Before I really get going, this is obviously non-exhaustive list, but just kind of listed out some advisors, supervisors, other folks, institutions and agencies that I've worked with. It's really fun to kind of get the opportunity to look back and see where people connect in and out and how often they come back and in what ways. Often different ways and sometimes the same, but slightly different just because your frame of reference is different. We'll kind of take hopefully a fun story arc through what I've been up to since basically really, really young age. As you'll see on the next slide, the Weather Geek really runs deep, but it ebbs and flows, right? Everything is an ebb and flow, and so I tried to weave this meandering river weather occurrence theme through here. So if those who don't really know me, I grew up in Minnesota, so the land of 10,000 lakes in a city called Lakeville. Very apropos because there's many lakes. There's one. This is the lake that's about 2.5 blocks from my parents' house. So I spent a lot of time at that park, on that fishing dock, catching bluegills, bass, etc. And then if I wasn't there or in other puddles of water, I was at home watching the Weather Channel often. So that's the Wayback Machine. You can find archives of things, which is great. So if anybody remembers, that's the old local on the 8 forecast. Kind of like just very good memories. I would stay up way past my bedtime watching the tropical update. So 50 past the hour. You might have Jim Cantori if you're lucky. Doing the tropical update, waiting for the next NOAA reconnaissance update to come in. And kind of this interest in weather also, this is a picture of me at 10 rocking the Stonewashed jean jacket. But my parents kind of indulged this weather and out kind of interest. We went to a lot of balloon rallies, so hot air balloons is kind of a really nice way to think about the weather. Someday maybe hot air balloon, someday. That's kind of always been in the back of my mind. We'll see. I've been able to take a few rides, and that was just kind of a point. And then when I got older, right, storm chasing, went to Colorado State, and this is outside of Wyoming, outside of Cheyenne in southeast Wyoming. This was like the perfect chase. It just sat there, didn't do any damage. We didn't have any damage, but very just picturesque. I think EF 2 or 3, but I digress. So kind of always being interested in the weather, that's the origin story. I didn't really have too much diversity and looking for schools, right? It was atmospheric science, weather, or bust. So the University of North Dakota is just up the road from the Twin Cities, about 5 hours away. It has a really good regional presence for meteorology. So really focused on synaptic dynamic meteorology, mesoscale meteorology, even studio broadcast meteorology if you want. But I think I probably had too much of a face for radio. So thus not the broadcast career. But yeah, my context was forecasting, right? That's how you often get into weather. If you don't come to weather from physics or mathematics, you come at it from just pure kind of the weather geek world, I think you often find. But perhaps lucky for me, I was introduced to research kind of my senior year of undergrad. Had some really nice experiences with faculty at UND and external. So this is a picture of an instrument called the Snowflake Video Imager, now the particle imaging package. This is a NASA instrument. But the cool thing about this experience is I was able to work with it at a field site, set it up, spend years with it really so I could learn the ins and outs and then develop all of the processing. So it was originally developed for rainfall, so it would take pictures of raindrops, right? But you could take pictures of anything, right? So we brought it to North Dakota with the idea of measuring snowfall. And the kind of the real key point of that is, given the way it is, the sample volume is somewhere out here, but if you run like a computational fluid dynamics software, which is here, so you can see the mesh of the light in the instrument, and this is the wind field. You can see the wind anomalies essentially aren't in the sample volume. So that's really nice for snowflakes, because snowflakes are essentially a tracer, right? So they just flit around. And so we also had a vertically pointing Doppler radar. All of my work at the University of North Dakota was this observation-centric on cloud microphysics. So building surface distributions and profiles to try to understand the evolution of snowfall. And then after that, I had this decision point: do you take a PhD opportunity or not? And so it's actually kind of challenging to find PhD opportunities switching between your master's and your PhD. Luckily enough to work with Dr. Richard Johnson at Colorado State, but he's a mesoscale modeler. He does observations, but a lot of his work was in kind of theory of mesoscale dynamics, tropical meteorology, and at the time he was doing a lot of modeling work. So that was very challenging. So stormy, right? So mesoscale meteorology, convection, but it was also a very challenging transition. I remember really struggling for quite some time on how to move from observations to modeling. But in the end, thankfully that worked out. Was able to do some really nice work in the North American monsoon. So moving from snow to subtropical meteorology, but getting to kind of enjoy the weather geekiness again. Thinking about mesoscale dynamics, so features like tropical upper tropospheric troughs, which is, I am advancing the slide instead of laser pointer. So this is an upper tropospheric feature. So this is 250 millibars, hectopascals. Essentially, these things rotate underneath the monsoon high. So the monsoon high is up here in, say, Arizona, Utah, Colorado, Nevada. And then these features come over, break, and then circulate back under. But you can see the wind speeds are shaded. The wind vectors are in the arrows. They enhance shear. They also have mid-level cold pools, and so they enhance instability. And then that generates lots of convection along the Sierra Madre Occidental, which then feeds into this next feature, which are Gulf surges, which essentially are kind of bore-like features. So we did some really nice modeling studies of that, where they propagate up the Gulf and then are precursors to the heavy rain events that you see in southern Arizona, because it preloads moisture into the core of the U.S. monsoon region. So I was able to advance understanding of those features, and then during grad school, I was also really lucky enough to be able to kind of meander around. So enjoying the field work in North Dakota, I was able to participate in 2 field campaigns that weren't at all related to my research, but it just was really fun to do. And I bring this slide up, not that I contributed great science out of this or anything, but to say that it's an experience of relationships and people and being able to like appreciate how things are done, right? So how do you get observations, and then how do you bring that to a modeler? You might recognize some faces on this picture. That might be me with a goatee. And then that's actually Paul Kuchera, who's over in Comet now. This is Dr. Greg Jenkins, who is at Penn State. And he hadn't arrived, but Everett Joseph was a faculty at Howard at the time. So little did I know later, right, that would come back around. So that's a fun little connection. And that's just me trying to fix our car that broke. Servicing the rain gauges, the exhaust fell off, so it was dragging. So we were trying to fix something there. And then I was also on Timrex. This happened when I was at CSU, and SPOL was there, and actually met people in the audience here, and hopefully are also online for the first time, which is really fun to think about as well. So like Tammy, Scott, Vibka, Mike Dixon I was looking through the EOL archive, we're on that field campaign. I didn't see pictures of me with them, but I think I have pictures somewhere to prove that. So then getting to NCAR, I remember my advisor, I told him I want to go back to snow for my postdoc, and he said, well, I don't know anything about that, but I guess I will support you. So that was another just like example of a positive relationship and experience where somebody was thankfully able to be supportive. So I somehow got into the ASP postdoc program, and then ended up with Roy Rasmussen and Martin Clark at the time. And this was in the 2011 timeframe. So the context at the time then was regional hydroclimate and climate change, Colorado headwaters, CONUS, but also thinking about really high resolution, right? So novel at the time were the high resolution regional runs. And there was a paper in the land surface hydrology world of hyper resolution, so sub-kilometer will solve the world's problems, so to speak. Maybe it wasn't that strong, but a lot of my postdoc work was using the NOAA-MP model, which is developed here and elsewhere, but thinking about, okay, say we had high-res data, so this is a catchment with 10-meter vegetation, we can generate solar radiation, we can look at snow drifts and wind sheltering. Let's say you had hyper-resolution information. If you then model the catchment, what does that get you for prediction performance? So this is just an efficiency score. Positive is better. 1 would be perfect. But then the number of grid elements, right? So it's the number of grid cells or elements in this catchment going from 1 to 1,000. So spanning several orders of magnitude. And we showed, so this is statistical significance on the skill of the prediction or reforecast or restimulation. And you can see there is no statistically significant difference between these really hyper-resolution versions and if you are smart about how you disaggregate the basin. So this really was bolstering, again, this idea that's been in the literature of hydrologic response units and how you don't need hyper-resolution for hydrology. Specifically, in the atmosphere, right, you turn off the convective parameterization, you might get improved convection because you turn off a parameterization, you resolve a process. In the land, you don't get that necessarily. You don't necessarily resolve any more processes or turn off parameterizations. Part of it is because you can't observe the land, right? It's very opaque. Part of it is that the scales that processes operate on are different, right? And so the idea that hyper-resolution, just blindly applying a grid to the landscape solves your problems isn't necessarily true. And we were able to demonstrate that there. So then, after a postdoc, right, you need to try to figure out what's next. So I think NCAR really embodies now, especially what somehow I was able to do, like developing this diverse knowledge in atmospheric science and starting to build out hydrology, land surface modeling expertise. And it was really fun to think about hydroclimate as a whole. And so how do you figure out what's next, right? You have all these different choices. Well, luckily there was, I wanted to stay at NCAR, and there was an opportunity. So this was work that's funded by the Army Corps and Bureau of Reclamation. Actually continues to this day. So this is like one of these nice, really long examples of long-term relationships of pushing the agencies and science forward at the same time. I need to be aware of time. So this really kind of, what you've seen up till now kind of forms the core of what I'm doing at NCAR. And so thinking about regional hydroclimate, precipitation, weather, observations, modeling, and applying that for agencies and specific use cases. And then recently I've been trying to think about how to synthesize this in the meaningful way so we can move forward. This kind of knowledge paradigm of iterative actions, informations, and knowledge, or the action, knowledge, information, AKI this paper. An information theorist proposed this as an alternative to kind of this hierarchical pyramid structure, which I like. Is all of our work is more iterative than hierarchical often, right? And so, information and knowledge can inform actions. Actions can inform and design new information, which then you build knowledge, and the cycle just repeats. And so thinking about those 4 core research areas in kind of that iterative, interconnected space, kind of have like this core theme that you've maybe been picking up on, regional hydroclimate, right? So water, the interface of the land and the atmosphere and the water cycle in kind of this regional scale. I'm definitely not a global type person, but a regional focused person, so local to regional scales. So that's the core concept, right? And then the knowledge information layer you could put here. So you have disciplines, you have tools, you have methods, co-production, statistics, et cetera. And then out here is really the action layer where you see the doing and the results, the outputs, the deliverables, the applications, use cases. And these are just examples you'll see more of. This is a gridded precipitation field of the Great Flood. This is a gridded temperature field of if you tried to represent urban heat islands, you can see them pop out. This is regional climate with emphasis on hydrology, right? So you have water, we just highlight watersheds. And then pure hydrology, you might care about stream flow. So observations and model comparisons to different iterations of the model. And we'll see pictures of these here going forward. So getting into hydrometeorology and data set, you've seen data set development. So you've seen a little bit of hydrology with the work during my postdoc. Towards the end of my postdoc and getting forward, really was lucky enough to work on projects that brought out my observational experience, setting up rain gauge networks, working with different observational data sets to work on how do we build the fundamental data sets that you need to do all your modeling and development evaluation kind of work. What are estimates of truth and uncertainty, and how do you understand processes across scales? So we're going to focus on 2 types. These gridded precipitation temperature products, right? So how do you go from stations to a grid that's continuous in space and time? And then thinking about hydrology, land surface modeling, specifically, it's often useful to operate at the catchment scale. So, what does a watershed do? How does it behave? But taking lots of them and trying to understand what the regional kind of variations of hydrology and hydrometeorology are. And they're used, again, across a lot of different applications: process studies, analysis of historical events, model evaluation, forecasting, et cetera. And so again, looking at the gridded products, this is kind of the question, what is the continuous spatiotemporal distribution of precipitation and temperature? But what does that mean, and how do you do it? So you have, different observation networks. You might have radar, even if you wanted to get fancier. But just starting with in situ observations, you have to go from sparse, irregularly spaced points to a grid. And so you can do that with geostatistics, Kriging. You can do that with multiple linear regression, multivariate regression. You can do all sorts of different things. So basically, there's many choices. There's lots of sources of uncertainty. And so how do we start to quantify that and understand it and use it in a meaningful way? And so building on some work that had happened now almost 20 years ago, 10 years ago now already, I was able to lead the development of this Fortran tool called the Gridded Meteorological Ensemble Tool, or GMET. And, we're at NCAR, so we all love good acronyms. There'll be several more good acronyms throughout this talk. But this is essentially one of the options that you can do is it's multiple linear regression. And the nice thing with that is kind of like Kriging, you can estimate your uncertainty from your regression framework. So either the residuals of your regression, which is an in-sample, or cross-validation. So k-fold or leave one out type approaches, right? So you have some estimate of your regression uncertainty. And you can include static in a multiple linear regression framework. So like elevation, lee, windward, so slope, aspect, location, latitude, longitude, things that might be important for where precipitation might fall and temperature and how that varies over space. And then you can also add dynamic predictors, right? So like Era 5, you could use as a predictor what is the precipitation temperature from that to bolster your regression model. And then I think the really unique thing, though, is then you can take this uncertainty and the regression estimates and build out ensembles. So sampling the uncertainty space in a coherent way. So spatially correlated random fields. So there's a 2D correlation structure determined from the observations themselves that then is applied to the regression estimates, and you come up with these different ensemble estimates. So if you look closely, you can see, right, these are different across the different members, the monthly estimates of precipitation from the flood, because they had fallen within the uncertainty space. And then you can look at things like the mean and standard deviation if you want measures. But there's also then every day, there's a continuous time series at every grid point that enables you to do a lot of cool things, which we'll see in a few minutes. So we have products now across all the 50 states, different domains. There's different advances that we'll talk about in a few minutes that go along with the different domains. We'll focus on Alaska primarily for a lot of this talk, but they're all available, the code's available. But then now we've taken this even further. So now Python, right, is a really great way for people to work in an even more flexible environment. So this is essentially the very complicated workflow of all of this in the Fortran and the Python version. So you can take input data of any kind, you do station processing, right? It's not important necessarily what is actually happening, but QA, QC, you get a station data time series, and then you do all your ensemble generation for the different variables. So precipitation, daily mean, diurnal temperature range. You can estimate your correlations for your spatially correlated fields, and then sample from your distributions and generate your ensemble members. And then you can even do corrections if you want. So all this is all implemented in Python. Some really great collaborators have done this this work, and it's really improved GMET, both in the code base, bug fixes, obviously. Now new products are coming out that are higher resolution, bigger and better. And so this is just an example. I've been talking about methodological choices. I'd be remiss if we didn't actually show one. But if you look at the new GPEP product, and then compare it to two other products, you can see these two actually agree, so it's not necessarily important what the product names are, but that this product then is different over the Intermountain West. And it goes back to the assumptions of lapse rate, right? So you have stations over complex terrain, they don't necessarily observe the peaks of mountains. And so what do? You have to extrapolate or make assumptions on how you get there. And so this product assumes a constant lapse rate, and in the winter, 6.5 K per km moist adiabat is too aggressive. Often you have inversions and other things, so lap rate's less than that. So this is actually then a little bit too cold at the highest elevations than what might be expected. Thinking about large sample data sets now, so now we have gridded meteorology. These data sets then use that. This again is this desire to unify uniqueness of place and generalize hydrologic theory. How do you uncover regional relationships? Well, you can't just study one basin for 30 years. You need to have a catchment, a large collection of catchments. And so this then enables regional studies, process studies, hydrologic optimization work. How do you best estimate your model parameters across complex terrain? How do you do predictability work? So what is it, initial condition versus boundary condition driven? All these things have happened with this data set. And so this is, the requirements are for something like this is, again, you want a large number, but you also want them to be diverse, right? So diversity of hydroclimates, process characteristics, and so this is just highlighting fraction of snow, right? The Intermountain West has more snow. The Southeast has basically no snow. You can look at aridity or other indices, and they're all, the PDF is very broad for this catchment base, and it's built off of the USGS hydroclimatic data network. So these are catchments that have minimal human influence, long records, so 30 plus years. And so that's important because you don't want to, at least in this case, we didn't want to try to predict human consumption, human interference. And so that's something that we avoided by using those basins. And this is just to show that it's now been picked up by the world. Imitation is the sincerest form of flattery, so there's other CAMELS basins. But CAMELS is the catchment attributes in meteorology for large sample studies. And it's kind of cute because camels drink a lot of water, store it, and then move it just like a catchment might store water in the headwaters and then move it down to the outlet. And will not take credit for that acronym. That was this non's a door, not a window. I learned that joke from Martin. He probably will hate me for saying that out loud, but he was really great with the acronym and the logos for this. And so that, I think, a snazzy acronym actually really enabled the data set to take off. But then thinking about hydrological modeling and applications, of those data sets. So really, you can do a lot of things when you have uncertainty estimation and ensembles for forecasting and projection. So this is an example of hydrologic model data assimilation, right? So you have an ensemble of initial conditions or states. You can also build ensembles of parameters within the model because you can optimize to using uncertainty. And then you can do ensemble Kalman filter DA, right? So this is just a really example just for snow water equivalent, a pretty simple case, but you can update your model states, right? You collapse the ensemble maybe because your observations are more certain, then you run the model forward. And all this is to say then on the trace, red and green was maybe a poor choice, but the red is the observed, green is the open loop, no DA, blue is the DA loop. And you can see they're different, which you would expect since the states have been adjusted significantly. And if you look at the statistics across many basins, so we use the CAMELS data set to do many basins, you can kind of see that you can understand where DA is useful, how is it useful, what do the increments look like. You can really try to understand the characteristics of what you would want to, how you would want to design a forecast system. So again, laying the groundwork for applied operational type implementations. And then on the climate modeling side, we all know we compare lines and plots of differences, right? But what does a difference mean? Is it meaningful? Is it statistically significant? So if you can quantify your observational uncertainty, you can identify areas where a difference might be meaningful. So anything that's hatched, so the differences between WRF and an observational data set are colored. Anything that's hatched means that it falls within the observational uncertainty. Anything that's not means it's a significant bias that you might want to pay attention to. And this actually turns out this is from the CONUS 1 run, if you're familiar with that. It's a regional climate run over the lower 48. And it had a really warm and dry bias. And I guess this confirms our expert judgment, but it's nice to see where we then spent resources for years on this warm and dry bias. And we didn't necessarily have to worry about differences in the coastal plain or the Pacific Northwest where our observations are very uncertain. So thinking about camels, like I said, this became amazingly popular. This is an example of unintended consequences where I didn't know about ML prediction models. I knew about neural nets and things, but this data set, since it provided all of these attributes, all of the meteorology, we also provided a calibrated benchmark model, which is very important. So you can a priori define performance expectations. The ML folks took this and ran, and even had papers devoted to talking about the data set, which I thought was funny. It's hard, kind of looking at this, it's hard not to kind of just laugh and not to be get big in the head, but it was just kind of funny to see this take off, and it's really cool, right? It's like a compliment again. But more importantly, the work that we did here with it is actually not shown for time, but you can then actually make progress on understanding your performance variations and where predictability varies and why, and then rigorous benchmarking. And so this is an example of that, right? So you have these outlier basins where you might, if you focused on just a few basins, you might get really confused as to what is a relationship, why are they different in performance, and it might be something that you just can't explain yet. But if you have a large set of catchments, this is a relative difference, so the benchmark is better if you're in the negative. Our target model is better if you're in the positive. And then this is a runoff ratio, so it's essentially how much of the precipitation gets converted to runoff. And as you get into wetter basins, the model performance varies. And we did some work on understanding why this is, but won't go into details on that. It's related to model structure. It's related to the hydrologic processes that the models capture based off of their structural assumptions. So trying to move along here, moving into regional climate modeling and downscaling. This kind of work, again, is really supported by the whole and really supported by those data sets, those capabilities. And this work, I think, is maybe a little bit more now, these days, near and dear to me. Not one, because I'm doing a lot of it currently, but also because it's becoming really community and decision-making focused. And these days, it's really critical that we keep this message and keep this work going. So how do we deal with extreme events? How do we deal with changes in streamflow runoff? And how do we actually support decision-making that's meaningful to communities and agencies? but it respects and supports the different ways that you have to get there when you deal with a dam operator versus an indigenous community. It's quite the dichotomy of styles. And so focusing on Alaska and the Yukon, because we've done a lot of work there, really now 15 years or more, just us. It's interesting that it's one of the 50 states, but it's underserved in that there aren't, in a relative sense to CONUS, a lot of products. So this initial work was funded by Army Corps, so large agency needs. Again, building knowledge, building observational estimates of precipitation and temperature, building regional climate models for projections and historical modeling, building hydrology models, and projections of water resources, things that matter to agencies and communities. So first, since now you're familiar with the GMAT, we can maybe kind of just give some highlights. We were able to add another methodological advance. So one of the predictors of daily precipitation could be the climatological field, right? So there's a underlying spatial distribution over long time periods. You can use that. That also has uncertainty, so we were able to extend the uncertainty estimation of that into then climatologically aided interpolation methods, and then also, particularly in Alaska, right, gauge undercatch from snowfall. It's windy, precipitation gauges are bad at measuring snow in the wind. How do you estimate undercatch corrections? Well, there's a lot of uncertainty in those equations, so we incorporated that into the ensemble GMAT framework. We did the first region-wide high-resolution climate simulations, not the first high-resolution climate simulations, but for Alaska region. We did historical pseudo-global warming, so Andy Monahan and I were able to do a lot of that work, and you can see the really complex responses and changes. So there's a really strong temperature signal, but in areas that's buffered due to the underlying climate or elevation, right? So the underlying hydroclimate, and you can really see that in the SWE, where similar to CONUS, areas that are high and cold actually can see increases in snow, but a lot of areas have significant decreases in snow. And then what does that mean for hydrology? But one really neat aside is there was a student from France who actually worked with Andy Prine. He got to do some weather geeky work, look at thunderstorms. So thunderstorms in Alaska actually do happen a little bit. This is actually a pretty good representation of the historical pattern from the model. So there's a few thunderstorm hours. And then in the future, this is RCP 8.5 PGW, so end of century, so it's kind of worst case. But there's a huge increase in thunderstorm hours. So that implies big increases in intensity of rainfall, right? And that's huge implications for infrastructure, particularly in the built Lake Fairbanks or Anchorage. So then thinking about downscaling in a statistical sense, how do you build out ensembles? So we started building out ensembles for Alaska using the CMIP5 model data. We were able to apply BCSD, it's the bias-corrected, spatially disaggregated method. It's a simple approach, but it's really effective and widely used. And so that stakeholders really appreciate it and understand it and know the behavior of it, right? So it's not something that they would balk at using. We're able to downscale 10 CMIP5 models, build out a hydrology model, build out projections of precipitation, runoff, snow, and everything region-wide, and then release it. So here's the runoff projection. You can see it's becoming more complicated where you have areas of decreases due to snow loss, areas of increase due to increased precipitation and snow melt. Really at the margins of the high terrain in this model were the most interesting. But again, in the end, this data now is out there. It's being used by folks in DOD. It's in the DCAT tool, which I don't remember the acronym, but it's essentially their climate. Can I say that out loud? It's still their climate planning tool, to my knowledge. The USGS uses it, national parks. It's on a lot of climate data portals for now. And then the second iteration really focused on the community aspects. You know, there's a lot of things we learned, but we learned obviously that we need to keep iterating on this. And so, you know, we thought it would be better to focus on the hydrology within the coupled model. So a lot of our regional climate modeling work was just kind of more atmospheric centric, right? Because we're NCAR. We brought hydrology in, so we spent a lot of time working with CTSM on how to optimize it for a specific region to do really good hydrology in the coupled land atmosphere model. I think that's a really nice advance. And it actually was, I think, a really nice thing for me personally, because I got to work a lot with CGD, which is a really great connection. Thinking about community-informed futures and domain and time horizons. So we spent a lot of time in experimental design with the communities. And if you saw my October talk, you saw a lot of this. So we spent a lot of time in co-design, co-production on that, thinking about different evaluation frameworks, adding river temperature modeling, river ice modeling, fish bioenergetics modeling. So this is all on this larger project. I didn't do those specific things, but the work that we did and I did enabled that. And that's really what the communities cared about is, well, what's gonna happen to my subsistence fishing? What is gonna happen to the king salmon, the Chinook salmon? Is it gonna even be able to live in an environment where every single stream reach is warmer in the future? And so if you don't know salmon, they're very sensitive to temperature. They actually have kind of a threshold temperature where above 20 C, they start to have heat shock and heat damage, and the bio, I'm gonna butcher it, bad things start to happen health-wise. There's a morbidity, mortality outcome above 20 C. So if you've read articles about the fish kills in the Yukon River, it was because of a temperature threshold event where they weren't able to find refuge. But on focusing back on what we were able to do on our project, so I led the regional climate modeling and dynamic downscaling. So this is some really nice work that's going to be submitted on Friday, I think, to BAMS, and it's been in other papers as some of the underlying analysis. You saw other references. But these are the climate zones across Alaska, simplified map, looking at just change signals and different metrics. So annual precipitation, the 1 day maximum for a year, then the 99th is a little bit more extreme, and then signal to noise ratio. So we did a small ensemble of dynamic downscaling now. So we went from 1 PGW to 2 PGWs, 4 CSM2 direct downscales. And we went from 10 years to 30 years for each of these. So increasing sample sizes, increasing the power of the data sets. And kind of the bar from the literature is the signal to noise ratio greater than 1 means you have more confidence in the change signal relative to the spread. It's a kind of an interpretive metric, right? I wouldn't necessarily say this is the definition of signal to noise ratio that you can rely on, but it's useful for interpretation where you can identify areas where all these precipitation metrics, right? There's a really strong signal. But then again, kind of confirming our initial, maybe simpler statistical to simple hydrology. Runoff is more complex because you have dynamics across temperature, precipitation, seasonality, how the snow impacted. And you can see the change signal varies by metric and region. Then the signal to noise ratio is often less than 1. The change signals might be weak, which is inherently then going to have a low signal to noise ratio. But I think these are really useful figures for quick dissemination of where information might be more reliable or more robust, depending on how you would want to frame that to a partner. Yeah, this is just to highlight the centroid. So this is an important metric in that this is the day of the year where 50% of the flow happens. So getting at seasonality changes. And you can see it's really a mixed signal across the state where you have some areas that are later in the year, some areas that are earlier. And this has implications for subsistence fishing and ice road travel. And then thinking about statistical downscaling. So again, bigger and better, thinking about uncertainty quantification. We were able to use a tool that actually was developed here by Ethan. It's another statistical downscaling technique. But I think Samantha's in the audience. She was able to downscale on a project that I was leading, 3 of the single model initial condition large ensemble. So this is really powerful in the way to add, if you're familiar with the SMILES, it's a way to understand internal variability in climate models and then across the models. So having multiple models do this then lets you understand model uncertainty internal variability uncertainty. Now with the downscaling, we can add the downscaling uncertainty to that. So we can really quantify the downscaling uncertainty. So you can make really complicated plots like this that have tons of really good information, but all that's to say is you can merge. So other deterministic downscaling products are these blue and purple lines. The observations that we train to are in black. This is diurnal temperature range. So you can see there's divergence in methods and the uncertainty changes over time. So you can try to start to understand why are these products different? How are they different? Does it matter if they're different? You can see the trends are different, right? They fall outside of uncertainty ranges in certain spaces. And so you can make decisions about which products you want to use and how to quantify your uncertainties. And that's all work that's ongoing. And so even talking a little bit more about action of all of this. So now all of these data sets are being released in various places, right? So this is on I guess this would be the highly technical users, right? Okay, they'll go to the RDA and download data, or the Arctic Data Center or Zenodo. But we also archive all of the different things for repeatable science. But then more meaningful to communities and agencies, working with folks like at Northern Climate Reports, where they develop plain language summaries at the watershed or locality scale, doing our own plain language summaries for the communities that we work with, thinking about how you aggregate and display the data, working with other large projects that have different community connections. So lucky enough to be involved with Rising Voices Changing Coasts, and so you can leverage and learn and build new connections for your actionability. So finally, this will be fairly brief. I think doing okay on time somehow. There's a lot. I appreciate y'all sticking with me on this kind of very large story arc. But yeah, so this is again, it feels very different, but it's actually not that different. It's different in the application, but how do you get to understanding heat stress impacts on morbidity and mortality? Well, you need to estimate exposure. How do you estimate exposure? You have to have estimates of temperature and humidity. Well, you either do that with your observation sites or you use gridded products, which are derived from the observations or a model. And so it actually was a really nice, just kind of happenstance. Was lucky enough to start working with Andy Monahan, as you saw. Well, then he was working with the health folks and then was brought into a proposal and then took it over after 2017. We'll just leave it at that. And was able to push it forward since then. And so I've been really lucky to work with, this is if you want to know how heat islands affect us, but essentially, right, it's warmer in the city centers at day and night. That's bad for health outcomes. But this is a really cool diagram that's from an institute in Spain. But yeah, so building relationships, building this flow of data, knowledge, expertise into actions with public health epidemiologists. Emory University, Yale University, University of Nevada, Reno are kind of the names behind the universities, plural here. And we've been able to develop a lot of work looking at heat and pregnancy outcomes, right? So acute exposure to heat while you're late-ish but still early or preterm can induce labor, which is a bad outcome. Kidney injury, right? You become dehydrated, you injure your kidneys, bad health outcome. Even fertility was explored. And then really the part that I was working on is leveraging all my observation modeling experiences to build in spatial representation of heat. And so, there's an open question of does it matter? Well, so some of these studies we were actually able to get health records at zip code census tract level. So you do actually want to resolve the spatial heterogeneities of heat and try to improve your exposure estimates. And so if you look at the products that are out there, so this is to aim at, it's again, not important to the name of it, but it's a product that's at 1 kilometer grid spacing, not resolution. So it's a grid spacing. So as folks in public health and epidemiology like DAMET because it's high resolution, but it uses a filtering mechanism to interpolate. And so it really doesn't even have heat islands in it at all. And LDAS would look something like this, where there's not really knowledge of urban areas. If you add an urban model, you get something like this. And so you may say, well, that's very sharp. And so I'll note why that's very sharp on the next slide. So this is the last really nice acronym. And I did come up with this one. It's the High Resolution Urban Meteorology for Impacts data set, still only data set, although we were working on making the S happen in the future, or humid. So it's no MP land surface model with an urban canopy model, so it represents the urban energy balance. But to do CONUS for 40 years at 1 kilometers, we chose to do it as a column model, right? So no advection, so not WRF, just offline land model. And you might say, why? Well, if you're familiar with how much the CONUS 4 kilometer runs cost, this would be 27 times more expensive approximately, since it's a 3 times 3 times 3 resolution decrease. And so that's really intractable, especially for a project that's only a few $100,000 big. So you make assumptions and you make what the decisions based off of user needs and do the best you can. And so I kind of fun to look at these and pick out where it's good and where it's bad. You can see all the urban centers highlight, but then you can kind of see it's very speckled. And so what's actually happening is all the little urban centers are also lighting up, which may or may not be that real. I think TBD on that. But you can see as you compare to DayMet, right, again, the urban centers highlight themselves because the difference, DayMet doesn't actually have them, although it's high grid spacing, it's not high resolution. And so immediately we can say, well, we have work now to improve that, to actually add advection at a more localized scale. So yeah, that kind of delves into future directions. So a lot of the things that I've shown are both uncoupled and coupled applications. I've become really interested in coupled applications, and I think it's important when it's necessary, right? It's not always necessary to have coupled applications because sometimes there just isn't really coupling that you need to care about. But if and when we do want to do coupled applications, it's really complex, right? It's CESM, how do you do that in a meaningful way and do it in a resource efficient way? So improving model diagnostics, model development efficiency, and then spanning the timescales is really interesting. So you can do things like with MedPlus, which is in-house here, open source software, model diagnostic software. You can contribute to it. So this is looking at a bunch of different land diagnostics that we're adding. So the terrestrial coupling index, the convective triggering potential, CPT, dash humidity index. So that gives you a phase space of, is it dry or moist, convective triggering. So all for process diagnostics, and then all in open source so that it can go back to the community. And then thinking about even more advanced stuff, so we're not gonna spend any time here, but this is this information theory, which is this really cool, I think, idea of signals processing where you can try to tease out how soil moisture is connected to maybe not, well, SWE's okay, that's an okay connection, right? How does SWE influence soil moisture? The chords or the ribbons tell you how strong the connection is. And you can do this in your models and your observations. And so we're trying to add that to things like MedPlus and really explore those. And so we have some work that's starting on that. AIML, right? We already talked about it a little bit, but this is gonna be bigger and bigger. And this is an AIML image of uncertainty in funding, as I took it from the water retreat talk last week, but it's really powerful, right? You can make a tornado on a table. But that's great scientifically maybe, but what does it mean for a partner? They're not gonna wanna use it if you can't explain it or tell them why it's better. And better is subjective for what they would desire and what we desire from a scientific standpoint. And then so that it would really then moves into uncertainty quantification and ensembles. How do we leverage AIML and physical modeling to really quantify our gray swans? How do we quantify the uncertainty of just day-to-day weather? And then how do we work with partners in advanced decision-making spaces? And then I think this is the second to last slide. But I think this one and then the summary slide really kind of wraps it up really nicely. I tried to kind of show that there's a lot of different things happening. You know, even if you're disciplinary, there's a lot of different things happening. There's a lot of different ways to think about problems. So how do we just increase our understanding and consideration of multiple ways of knowing? And this is, you know, I feel like I'm appropriating that statement, but really the indigenous communities are really leading the charge on, you know, local knowledge, indigenous knowledge, and multiple ways of knowing. And actually acknowledging that that's helpful more so, just more and more. How do we build respect and protect uniqueness, but also generalize our theories? Because we can't do We might be able to, but we really, I don't think, can go block by block by block and build solutions. We have to figure out ways to scale some of this stuff. So how do we do that and still respect uniqueness of place? How do we build teams? How do we build trust? And then that really opens the door to all the things that we want to do, I think. And so, yeah, I've just been really fortunate, have a lot of good fortune, to quote Dr. Dan Wildcat, to work with the people I've worked with, to work on the things that I've worked with. And I think I've been able to build out a lot of different cool things and, iterate and keep going, keep learning. So yeah, I'll stop there.
Hey, yeah, great talk, Andy.
Thanks, James.
Yeah, so you talked a lot about capturing uncertainty in various aspects and analytical downscaling, statistical downscaling, but you didn't really touch a lot on how that works for capturing uncertainty of extreme events. Can you talk a little bit about that and how to do that, and can we do that?
Yeah, I didn't talk about it a lot because admittedly, I don't think I personally have done enough work in that space to do it well. It's something that we're aware of, and I think it's implicit in our work, but I don't think I at least haven't done a good enough job on highlighting it in my work. So we're doing that now. There's some work that I didn't show that's really trying to focus on extreme events and building ensembles. It's really a sample size problem, right? It's like, by definition, it's extreme, and so like, it's the 1 in 100 or 1 in 1,000 or 1 in e to the -7th for dam safety. And so what we did on the dam safety work is really we brute forced it. And so we had simpler models. So we ran thousands and thousands of simulations and then did uncertainty analysis by ANOVA. So I guess I did do that work for hydrology, at least. That's funny, I forgot. I even have slides on it. Yeah, so here, so 1e to the 5th, what does that mean? That's a 100,000 year return period, okay. Yeah, have we ever observed that? No, humans have not been around long enough to really even, maybe you see one because you're lucky. But how do you do that? So you assume distributions, you do a bunch of probabilistic modeling, and then you can do ANOVA analysis here and partition. This is really for a partitioning of uncertainty. So an agency like Reclamation wants to know what is irreducible, what is reducible here. And so there's lots of fancy lines, but this is the precipitation input uncertainty. This is the initial condition uncertainty, and those are often the most dominant for extreme events. And so then you can try to go back and say, do we think that we can reduce that uncertainty? And maybe you can, maybe you can't, and that can direct resource investment or future research. So that's one way we've dealt with it. And then we're doing more kind of in a similar vein on doing event downscaling multiple ways to try to quantify what we think our uncertainty is for an extreme type event.
Let's go to online. I have to get closer. I think this is Tim, probably Schneider. Amazing body of work that you shared, Andy. Would be interesting to compare the single column humid data versus the C404 WRF sims. Have you thought about or done that yet? There are likely configuration differences, e.g. the urban components you included, et cetera, but could be insightful nonetheless.
Short answer, yes and no. So yes, we've thought about it. No, we haven't done it. So for folks who don't know, C404 is CONUS 404. So it's 40 years at 4 kilometers. That's the snazzy name. So I think the big reason why I'm hesitant to do it is that the 404 urban model is a bulk urban model, and it's really hot. We could do it. I don't know enough about the bulk representation to even know if it really has enough process representation to make it make sense to do. I worry that you would just say these are different and not really be able to diagnose why. But if there is a way to get insight out of it, I definitely think we should do it. So yeah, we haven't thought about it enough yet, I guess.
Thank you. Anyone inside here? More questions? Go ahead, Dave.
We had a comment about the high resolution data set. I'm blanking on
Yeah.
the name. Where you said it's grid spacing is high, but its resolution is actually low.
Yep. Yeah. DAMA. Yeah.
Yeah, damn it. Yeah,
Yeah,
sorry.
yeah.
My brain just lost it. But I guess I'm curious, do you have any examples of people misusing that sort of unrealistically high resolution, or thinking they're using high resolution when they're not?
Yeah. I'm sure I can find them. I don't have any off the top of my head. I can think of just where we as general need to be precise in our wording, where we say resolution, and even like WRF, and I'm guilty of this, and I think I just said it there, 4 kilometer, maybe I said resolution versus grid spacing. Well, WRF at 4 kilometer grid spacing doesn't have, and the effective resolution is like 7x. And so then I think any kind of process you're looking at that's less than 7x, you're technically misusing the data. For DAMET, I think there's a lot of, and I'm not super familiar with the literature, ecologists love DAMET because it kind of was the Peter Thornton, I almost said Peter Lawrence, but Peter Thornton, the developer of DAMET, came from kind of that ecology world. And so they love the high resolution. And so they're probably always misusing it in areas like Iowa, where there's a few hundred meters in elevation change. You can go zoom in on DAMET and you can see all the ridge valley lines. And it's like, I don't know if that's real or not. It might be, but I think they do a Gaussian filter, and that just inherently has a longer length scale. And so I would expect that some of that is kind of misuse, maybe not in a wrong conclusion sense, but in a strict sense.
No one online? Anyone else in the room? Rich?
Yeah. So, the work that you do is great, and the fact that you've moved it beyond just like averages, and we're looking and the uncertainty. I mean, a lot of people are like, well, we can't do anything with these averages. We don't know the uncertainty. And then you give them a measures of uncertainty, they don't know how to use that. And I'm wondering if you've experienced an extra step in terms of holding people back from using the uncertainty incorrectly, as well as the kind of gridded means.
I've certainly experienced the holding back part. So GMET has not quite had as much uptake as we had hoped because it's an ensemble. People just want a deterministic. Yeah. And so we've had to build our own demonstrations of applications and build our own test beds and try to really build it out. And the way that we've tried to make inroads is at the community level, it's really hard. It's almost impossible. But at the large agency level, you can make inroads because they have capacity. I think that's kind of the trick is, in my limited experience, when agencies like Reclamation and Army Corps move, then the city level utilities move, and then it's kind of a trickle down effect, because then you can develop methodologies and guidance documents and simplify things and kind of get people to be comfortable with it, and then have a way to use maybe synthesis or frameworks that exist. So that's kind of maybe how I would approach it more generally.
Okay, I think we have time for one more question. We'll go to the remote. Kim Vulis, how might NSF NCAR support ongoing engagement with the user community in order to maintain trust and ensure usability? What do you think is key, especially given the soft funding basis of RAL? Yeah,
good question, Kim. So NSF had been moving in that direction a little bit with new directorates like TIP and some of the initiatives like the R2, I2. So it was essentially a climate resilience at the community level program. How we've done it in RAL, right, is sponsor driven, right? So I also feel like this is not novel in a lot of ways. If you go back to the wind shear and FAA, it's really was all driven by specific needs and at a relationship level and an application level. And so we need to just keep doing that. Army Corps and Reclamation have been really great partners. They do a lot of cool stuff. And I think what we've been able to do is then take that and then go to NSF and get money for community work, community-focused work. And so like, how do you leverage and how do you find opportunities to do the things you want to do is tricky. It's kind of by feel.
Do we have time for 2 more questions? I hate to have unanswered
That's
questions.
a really good question from Hope. I don't know how to answer Hope's question.
Okay, we'll go with Olya first.
I want to talk about it, but
I think she was first.
yeah.
Great talk, Andy. Building on your work on identifying and quantifying uncertainty in models, where do you see research on visualizing and communicating uncertainty going?
Yeah. That's a good question. I don't know if I have a good answer. I think we have to think about bringing in people like Olya who asked the question, right? Is like, how do we visualize things? That's the hardest thing. I'm pretty basic on my visualization, so I just like to see shaded bars, right, of uncertainty. But it's maybe not what other people want to see. So yeah, doing like, like what Olya is good at, focus groups and really understanding what is needed by a specific sponsor or partner is one way. Maybe using AI/ML to generate cool tornadoes or n-dimensional graphics that we can only hope to understand in the future. I don't know. Could be something fun. Yeah. So
you have a few FTE hours for Olya?
Yeah. Yes.
All right, absolutely. The last questions online from Hope. Thank you so much for presenting your interesting work. Given what is happening to Indigenous organizations in this political climate, I want to ask, how can we continue to uplift Indigenous perspectives in science? Easy.
I think we need to be as strong allies as we can. So this is one thought. We need to be as strong allies as we can be. We're going to probably have more, can I even say, we're probably going to have more censorship, so we need to keep pushing the bounds as much as we can. We need to go to place, and I admittedly haven't done as good a job as I should, but I was able to go to Haskell Indian Nations University last week for a project meeting, right? I'm a bit player in the RVCC project, but it was really just good to see people in person and understand. And, it's just a different perspective. You really, it's good to do, and it helps everybody kind of band together. We need to work as a team through this period in time more than, it's easy to devolve into fighting for resources, but the collaboration will bring us out, hopefully.
Okay, thank you very much.